Here we are, it's the physics video lecture. Physics 4B video lecture 6. And we had so many questions about homework problems that we'll just do a big homework review right now and then see how far we get. So I had questions about the exponential atmosphere, and then chapter 20 problem 39, and then chapter 18, 29, 40, 42, 48, 49. And actually quite a few people asked questions about these. So that's good. Let's start with the exponential atmosphere. The question seems to have been mainly about integration by parts. So I'll remind us we had the average position for a distribution, which was the particle density as a function of elevation above sea level, 0 to infinity. So that would be enough actually if the denominator were just 1, but the denominator hasn't been normalized yet, so we need n of y dy. Okay. So yeah, what do we get for this? We have n of y is equal to n0 e to the minus mgy over k Boltzmann temperature. Okay. And if you wanted, you could write e to the minus a times y. A would just be mg k Boltzmann t if you want to simplify things. So this one's just going to give you a basic, integrate the exponential, make sure you do the lower boundary, upper boundary minus the lower boundary. Okay. As far as the integration by parts goes, let's write that out first. Well, actually, let's just make sure we see how this goes. So integral n of y dy. That's the integral. We can pull the n0 out front, 0 to infinity, e to the minus ay dy, n0. So then this 1 over negative a, e to the minus ay, 0 to infinity. Of course, the upper boundary gets killed by the exponential here, and the lower boundary evaluated at 0 is just 1, so that is just equal to n0 divided by a. Okay. And then you can plug that in when you're done. Now, as far as the numerator, you have to do the integration by parts. Let me just remind you, if you had d dy f of y, g of y, I'm just going to derive the integration by parts formula and then explain it there. So you'd have f prime g plus f g prime, and you integrate both sides of this expression. You integrate both sides and rearrange the order. So we'll take this one on the left, so you have the integral of f g prime dy, a to b, is equal to integral of this, of course, is just f g upper lower upper bound minus integral f prime g dy, a to b. So yeah, you write down our integral. We can cancel out the n sub 0. We're not worried about that one. So we have y e to the minus ay dy. Okay. 0 to infinity. So what we have to take as our g prime is this function right here. So if this is g prime, we're looking at y e to the minus ay divided by negative a. Okay, that's our fg. So that's our g, 0 to infinity, minus, now the f prime, since f was y, that's just 1, and then we have e to the minus ay, etc. So you're actually going to get another power of this in the denominator when you do this integral. But since f prime is 1, right, you're just going to have this under the integration, under the integral sign. So this here, evaluated at infinity, e to the minus ay, suppresses the y here. And then evaluated at 0, you just have a 1 here, but y equals 0. So this equals 0, and then this next integral will give you your answer. You'll just have another power of a. Instead of a, you'll have a squared. And when you rearrange that, you'll get the answer that we had. This is going to be K Boltzmann temperature over mg. And then the punchline, so to speak, was that this is going back to that lecture, K Boltzmann T, right? But this here is an average potential energy, and an average energy amount, K Boltzmann T, turns out for all degrees of freedom. Good. So that was the question, and I think it really just hinged on the integration by parts. So you can see why this one vanishes here, okay? Vanishes for the 0 there, and then for the even the minus infinity vanishes up there as well. Good. So that is from the exponential atmosphere. What do we have next on our list? 20, problem 39. Now that must have been, yes, the heat transfer by conduction in this little interesting configuration. So let's do this conduction. So you start with the idea that you've got some slab of material, okay, and then we have the formula I. They're using the letter I, that's power, okay, that's dq over dt. So that's power, and you got a minus K, which is just the material constant, surface area A, d temperature over dx, where that's the temperature gradient. And you'll often run into the same type of formula where they just want to give you the magnitude, and then you'll say Ka delta T over, say, delta L, where that's a thickness. Okay. But we're going to use this one, and here we're using it in a sphere with radius r sub 1 and r sub 2, so there's a hollowed out sphere, and we have a temperature T sub 1 here and T sub 2, so T sub 1 between the inside and the outside. Okay, so this is an interesting problem. What you can imagine is that, say the temperature on the inside is higher, so the heat flow is towards the outside, and at any concentric spherical shell in between there, the energy or the power, the energy flux or the power is going to be the same as it goes from inside to outside. That's an energy conservation type of idea. And so to account for that, we're thinking of this as a constant in the problem. That's the constant energy flux. And what we have now is minus K, but a shell here has the area, it's like since it's very thin, we think of it as a slab, but it's wrapped around as a sphere. We have 4 pi radius squared. Wherever we are r between r sub 1 and r sub 2, that's k 4 pi radius squared, and then the gradient in the temperature is with respect to the radius. So what we're going to do is separate variables. So the separation of variables is going to function like this. We're going to, I'll keep I right here, cross multiply over dr divided by r squared. Okay. And what's left on the right side is equal to minus k dt. Okay. So I just treated these algebraically, but this is a differential equation for r essentially. So on the left side, dr over r squared, cross multiply. And what we're going to do is integrate from r1 to r2, and here we're going to integrate from t1 to t2. That's what separation of variables means right here. Now the right side is going to be trivial, minus k t2 minus t1. The left side, okay, how about I do this? The left side. So there's our answer here, but we want to get this integral working to the left. So we've got I, which is a constant, comes out. And then we have negative 1 over r is the antiderivative for this 1 over r squared. So we have negative 1 over r, and the boundary is going to be r1 to r2. So it'll be negative 1 over r2 plus 1 over r1 when we do that integral. And now we just have to simplify. So we would have I times r1 minus r2, r1 times r2 is going to be equal to minus k t2 minus t1. And let's see, how did we finally want to rearrange this thing in terms of I? So finally, I is equal to, yeah, we'll just pull a minus sign out of here, so we'll have r2 minus r1. Did we keep the minus sign on this? Okay. Did I get this right? Got a minus, got a minus. Up to a sign. Equals minus k cross multiplying r1, r2, t2 minus t1 over I may be off by a sign right here, but you guys go look for the sign, okay? Oh, I see. Okay. Leave it there for now. You guys check out the sign. Good. So, what's next? What's next is calorimetry. And I said 18, 29, 40, 42. Okay, I'm going to consult the book on these, see what they were about. So chapter 18, number 29. Yeah, quite a few people wanted that one. So let's see what we've got here. How much heat must be absorbed by 60 grams of ice? Transform it to 60 grams of liquid at 40 degrees Celsius. Okay, good. So here's one of these where the Q total is what we're just calculating. So Q is equal to, this is not a calorimetry problem, this is just latent heats and so forth. This is Q of heat the ice, because the ice was at negative 10 degrees Celsius. We want to turn it into a liquid water at 40 degrees. Okay, I'm not going to plug any numbers in on these problems. So we have to heat the ice, then it has to melt, and then we have to heat the water that used to be ice. Okay, so this is just going to be some total number of joules. It will be the mass of the ice, the specific heat of ice, and then the final temperature is 0 degrees. The initial temperature is negative 10 degrees Celsius. So you see where negative is positive. It's a positive quantum. It's our delta T. We're going to melt the ice. That's just going to be the mass of ice times the latent heat of fusion of the ice. And finally, we're going to heat the water that used to be ice. So that's still the mass of the ice that was given there. Specific heat of water. T final, whatever that is, 40 or something, minus the 0 degrees. Okay, so this is going to give you some number. Okay. Next we have problem 40. Let's see what problem 40 was all about. This one is calorimetry. And this one had part A and B. Yeah, this one was interesting. So here's what we're going to do for calorimetry. So this is problem 40. We're starting out with ice at 0 degrees. Okay. So, and I did Celsius first, they have Kelvin. Let me just write this down. So the mass of ice times the latent heat of fusion plus the mass of ice, but it's now water, so specific heat of water, T minus 273 Kelvin, because we're using Kelvin here. The delta temperatures doesn't matter, plus mass of water, specific heat of water, T minus 303 Kelvin. Okay, so those are energy quanta. Okay, energy plus energy plus energy. In the calorimetry problem, it all equals 0. Okay, because the energy that came from the water is what melted the ice and what heated the ice up in the first place. So yeah, I like to set these up so that the total energy is 0 and the final temperature will take care of itself in terms of the signs. So another way to do them, you balance one side with the other, but this way the signs will take care of themselves. Now, so for part A, this is how you set it up. For part B, they gave you such numbers that there actually was not enough energy in the water to completely melt that extra larger block of ice. Okay, so I calculated the numbers. So for this was for part A. For part B, let me tell you what I had here. I had to compare melting that half a kilogram of ice. So mass of ice, latent heat of fusion, so we had 0.5 kilograms times the 3.33, that's a 3.33 times 10 to the 5 joules per kilogram. So you get 1.67 times 10 to the 5 joules, okay? That's what it's going to take to melt that entire ice block. On the other hand, the heat that's available, I'm just going to write water, is mass of water, specific heat of water, times delta T, and that delta T was just 30 degrees Celsius. So I came up with 1.26 times 10 to the 5 joules. So which one is bigger? 1.67. So to melt the entire ice, we would need this much, but there's only this much available in the water before the water is 0 degrees. Therefore, the conclusion is the entire block of ice is not going to melt. You're going to be left with ice in water at 0 degrees Celsius. Okay, or 273 Kelvin, whichever you prefer. So yeah, the answer here is the entire ice doesn't melt. Therefore, we have, remainder of ice in 0 degree water. Yeah, so those are the types of problems where you can't just use this formula. You actually have to calculate these energy quanta to see whether the entire thing actually melts. The initial problem, that ice was sufficiently small that it was going to completely melt. Good, so that's problem 40. And what else do we have here? 42, 48, and 49. So 42 is just a calorimetry problem. No latent heat diffusion. But yeah, since someone wanted that, I'll write it down. Now 42 is the kind of problem that there are just a lot of numbers involved. So conceptually it's not difficult, but punching in that many numbers, what can possibly go right? So let me consult the book here. 42. Yeah, we've got a mystery substance, determine the specific heat, and then we have a bunch of masses and temperatures. And we want to determine the specific heat of the block. Let's see what I have here for this, or do I have it? Yeah, here's what I have. Everything's going to add up to 0. Okay. So the sum of all these Q's is going to add up to 0. So you write this thing out, you've got the mass of the block, specific heat of the block, final temperature minus the initial temperature of the block. And then you have however much copper you have there, specific heat of copper, T minus the initial temperature of the copper. And then you have some water. We had two water here, so water 1, specific heat of water, T minus T1 for the water. And then we had the next water sub 2, specific heat of water, T minus T sub 2. Okay, so that equals 0. And it's one equation, so you can only solve for one unknown, and all these temperatures were given, and what we wanted was the specific heat of that block. So conceptually, no problem. Practically, punching in a lot of numbers. But actually, in terms of the physics, this statement is important. What we're doing is we're isolating that system, and so there's just energy exchange. There is no energy gained or energy lost. Okay? Just being exchanged and transformed from one substance to another. Okay? That's part of the content of energy conservation. Energy is neither created nor destroyed. So along those lines, that's kind of what I'm going to end with on this discussion here. I just brought it up that the energy is not created, not destroyed. It just changes forms. So since we put a total amount of, we put a bunch of stuff, imagine we sealed it off in a box, and all that's going to happen is energy is going to flow from one thing to the other. That's why I like to set them up here and set it equal to 0, because in the case of an unknown temperature, it will just adjust itself. The unknown temperature will take care of the signs. In this case, they gave you all that stuff. Okay, so what do we have on 48 and 49? 48 was really basic. We've got a bullet, and it's gonna, hit a plate, maybe a steel plate or something. The idea, though, is that this bullet just has kinetic energy, and that's going to be converted to heat. Okay. And what they did was, so it's going to be an MC delta T type of example. Okay. So this is all kinetic energy thing goes splat and just is converted to heat. And to be concrete about this, it was mass of the bullet, specific heat of whatever it's made of, and then that's T final minus T initial. The initial temperature was given, the final temperature was a melting temperature, so you had to look that up. Okay. And then you get, so that's that's again conservation of energy. What we had here was kinetic energy was turned into, so we could write kinetic energy converted to thermal energy. Okay. So conservation of energy. And that's, that's how you set the problem up. Let's see, what was our last one here? Problem 49. Yeah, so 49 was a similar one. And I'm going to come out with the conservation of energy theorem right here, because this is the general first law of thermodynamics. Okay, it's really conservation of energy. In our text, it's going to be heat and work in terms of pressures and volumes, but more generally, energy is conserved means conservation of energy. When you were just doing mechanics, that bullet had kinetic energy, and then we said the energy was lost, right? It's not lost because this thermal energy, could be thought of as microscopic energy. But yeah, definitely not lost. So conservation of energy means energy is neither created nor destroyed. Okay, it's that simple. Neither created nor destroyed. So when we talk about the first law of thermodynamics later on, we're actually going to be talking about this very general energy conservation, and then later we'll talk about pressure volume graphs and things like that. Energy neither created nor destroyed. That's the whole, and that is the first law in its most general form, thermodynamics. But remember, last time I talked about the second law, we hadn't had the first law yet. Okay, it's very generally speaking conservation of energy. So let's look at this last problem, which was actually pretty interesting as well. So problem number 49. So this one I think I'll read it for us. You warm your hands by rubbing them together. They give you a kinetic friction, normal force, average relative speed, and then the rate at which mechanical energy is dissipated, and then how long must you rub your hands together to produce a certain increase in temperature. So it seems like there's a lot going on, but this is a very basic problem. When I assigned it, I didn't even see how good it is, but now I do. Okay. So here's the thing. We're going to talk about energy dissipation, power. Okay. That's work per time. We can also call that force times displacement. I'll just keep going here now in symbols, divided by time, okay? Force times displacement divided by time. And you can say force, they're talking about an average speed, so force times velocity. So that would be power. That would be measured in watts, okay? So we have power is force and velocity. Now, they tell us about a friction law, and so you have to remember the force of friction is a mu here, the coefficient of friction, times a normal force times the speed. So there we have actually the power, the energy dissipated, the rate of energy dissipation right there. Okay? So I'm going to number this. This is the first aspect. Now the other aspect of power is that it is work per time, or energy per time. But we can also say it is thermal energy per time. So this would be power, you know, just mechanically, but this would be thermally, okay? Q over T, okay, so joules per second, right? So watts would be joules per second. So from this way of looking at power, we have time is equal to Q divided by P. So that is our second expression. And now you can see how we're going to put them together. We're going to solve for the time. Okay, put it right here. So the time that we're looking for is equal to MC, change in temperature. Okay, that's our Q. And the power we just had here, mu times N times V. This is also a good example where you don't want to plug in any numbers till you've actually figured the whole problem out. And then you see they gave us, you know, this is the mass of your hands and their specific heat, and then the difference in temperature that was given to you as well, and then U and N and V were all given. So that'll be the time in seconds if you use the correct units here. Okay. But important energy concepts right here. Okay. Power being dissipated as heat, Q over T, and this is literally just the work that you're doing to generate that heat per time, right? Work per time. Okay, good. So consult with the clock, see how much time we took on that. Okay, it's great. We've got nothing but time. So now we're going to talk about heat engines. I'll do a little bit of review of what we had done to get us up to speed, but we did get this conservation of energy discussion in, which is really important. First law of thermodynamics, and these examples are perfect for it. So let me explain where we're headed with this. We had talked about energy and entropy. So let me just say a couple words about energy and entropy. And then we're going to go into heat engines. Okay. Heat engines. And this is supposed to be really the most basic way to understand this stuff. So for energy and entropy, we've now seen we've got the first law of thermodynamics, which is called the first law, and that's conservation of energy. So energy is not created or destroyed, it's changing form. That bullet example was perfect. You had kinetic energy turned into thermal energy, turned into heat, but we've got that equal sign to tell us that nothing was lost. course, in reality, the bullet melted, but since it hit a steel plate, it actually, some of the steel plate itself was warmed up locally. Those are details. So the principal statement, though, is that it was all converted to heat. Again, the details could be that some fragments got blasted off every which way. Those fragments would still have half m of, some delta m, some v squared as well. So the first law is that the energy is conserved, and just every small piece of energy, if you add them all up, and you still have what your original was. That's the idea. Okay. So first law is conservation of energy. And this is good to realize before you go into all kinds of chemistry and other details. Just to hold on to that. Second law was that, so here's our first law. Our second law was a little more subtle. It was that the entropy, that is to say the disorder of a system, so delta S total of an isolated system is always increasing, at best 0. Your book will talk about reversible processes, okay, and things like that. Delta S total greater than or equal to 0 for an isolated system. And that's why our example was that, we drop into a perfectly insulated cooler, something that's hotter, something that's colder. Eventually the temperature's going to equalize. Energy is going to flow from the hot to the cold. Okay. So this also includes the direction of heat flow from hot to cold. And you can say it's equivalent, except this is much more general because it also just involves mixing of things, reactions, etc., every possible way. But our example was the direction of heat flow. Okay. So those are the two laws that are going to govern heat engines at the most abstract level. So what is a heat engine? A heat engine is a mechanism to obtain work from thermal energy. So heat engine, we want to obtain work from thermal energy. So obtain work from thermal energy. And we have that mechanical equivalent of heat, and this is a good thing to remember. So the mechanical equivalent of heat, I'm going to write it down, mechanical equivalent of heat was simply this: 1 calorie, back to talking about the calories, 4,186 joules. And of course, once you have this mechanical equivalent of heat, you don't even have to talk about calories anymore. Okay, you just talk about joules. However, it's useful to remind ourselves of this, because here we're just thinking pure thermal energy, we burn some fuel or something, and here we're thinking mechanical energy in terms of work. That's the reason for me to repeat this thing here, to remind us of it. Now the thing is this: what we knew so far was we could turn work into thermal energy, just like with that example up there, with actually the one that I erased with rubbing our hands together. Okay, that was work turning it into warming up our hands. And basically the mechanism was friction, although we see here it could also be a collision. Okay, this example up here with the bullet means it could also be a collision. But since we want to obtain work from thermal energy, what we're really asking this time is, how can we do this direction? Okay, this is what we're trying to achieve. We just want to burn some fuel and other process and get some useful work out of it. Okay. So yeah, if you go back to the mechanical equivalent of heat, this direction we, get fair and square, it's via friction, very important. But now what we want to do is obtain it. So we want to have the thermal energy here and get the useful work there. And I brought a little steam engine to class. So the next thing I'm going to do is direct the camera on it and see if I can fire it up. Okay, that's our little steam engine. So it has some solid fuel here, which I'm going to start with a later. Wish me luck here. Okay, good. We have a flame. Where I burn myself, I'm going to put it in there. And we're going to have to wait a couple minutes and see if this thing fires up. In the meantime, I will sketch what's going on there. Good. Okay, I'm going to have to sketch this. Let's see. That's heating up. That's good. Okay, the idea is that we have fire a boiler with a window in it. Water inside. This may not be visible, but it will be in a minute. We have a cylinder with a piston inside. This thing is ready to rumble. Okay, now everybody knows what they want for Christmas. Hope the fire alarm didn't go off. Okay. So that was a functioning steam engine, but it's not the only type of heat engine. But for the moment, I'm just going to label this a bit. So we have fire down here, we have a boiler. Okay, we have a boiler, and there is water vapor in here. Because it's going to be under pressure, it's going to actually push this we've got a piston, we've got a connecting rod, we've got a flywheel. And the idea is that this gets pushed out here and turns the flywheel. Of course, the question is, how do we get the thing to turn a complete turn? And in fact, we need a valve to release some pressure with every cycle. So every half turn or every complete turn, the valve has to have opened and closed once. So that's the heat engine, but it's not the only kind. So this is a steam engine. The other engine I wanted to show you guys, but I'm just going to mention it, and you can look online and get some pictures. So this is the first one. The second example is the Christmas pyramid. So if you look up Christmas pyramid, what you'll find is an interesting, seems like a decorative thing. You got a turbine here, you have candles, and the hot air rising from the candles drives the turbine and actually does useful work as well. I actually own one of these, but I don't have it here right now. Okay, but actually it makes a nice demonstration as well. So you got the Christmas pyramid. That's one type of heat engine because the hot air rising spins the turbine to do useful work. This device here that I just showed you is beauty. In fact, I think you all saw that the light was going on, so we had the connection to a generator and a little light bulb as well. Okay, so this is your civilization right here, okay, or it was your civilization. Actually, power generation is still via heat engines, but the more modern ones are actually closer to this than they are to this. Be that as it may, I think that's about as far as I'm going to get today. Let me consult. Yeah. Let's see here. I had some homework to put up. But I haven't quite gotten there. Well, here's what we're going to do. We've got these two types of heat engine, so just as a demonstration. Our question is, how much of this energy can be converted into work? So the question on both of these, how much of the available heat can be converted to work? That's the big question mark. And that's going to take a little bit of doing to set up. So, we have 4186 joules for every little speck of calorie. That could be fuel, that could be butter, that could be oil, that could be whatever. Okay, gasoline. How many of those can we turn into work? That's the question. Okay, I'm going to leave that until next time and set the whole thing up again. Until then, I'm not quite sure if we can do these homework problems yet. Let's have a look. We're in chapter 19. These were heat engine problems, so haven't quite gotten there. We're going to hold off on that until next time. Okay, we'll hold off on that. But yeah, we'll pick up with these two. I have to say a few more things about these before we work our way into the efficiency. All right, see you guys next time.